Did you hear about the Italian chef who died? He passed away. What's up, AS Math? It's Mr. Knight, and we are going to be taking a look at trigonometric graphs. We're actually going to be looking at the sine and cosine graphs today, and the reason I start off with a pasta pun is because we're going to be cooking today. Not really, but we're going to be cooking up some notes with some pasta, okay, with some spaghetti. So, where does the graph of sine actually come from? Let's assume for a second I have an xy axis, right? But instead of x, I'm using theta for my angle, and my y-axis is going to be, well, sine of that angle, right? So what I'm going to do is, I'm actually going to look at my unit circle. My unit circle is going to help me. And if we're graphing sine, what I can do is, I can actually break off pieces of spaghetti and measure it out, and try to see at each of these angles how high that spaghetti is going to be. Okay, this will become obvious in a second why I'm going to do this. Okay, really why I'm doing this is because I know that sine theta corresponds with the y-coordinate here, right? So the y-coordinate is literally measured, if this was a coordinate plane, the y-coordinate is literally measured from the x-axis right down here, right? So y is up here, y is up here, and y is here. And in fact, those are the lengths that my spaghetti is going to be at each of those angles. So, let's start breaking off some spaghetti. But first, where does pasta go to dance? The meatball. Alright, spaghetti. It's time to go, okay? I'm going to measure this out the best I can. Let's see, break it off about right there. I am a professional chef. Look at that. All right, so that is going to be at 30 degrees. What I'm going to do is now I'm actually going to place that at 30 degrees right there, just like that. Okay. Now I skipped 0. The reason I skipped 0 is because, well, there is no length, there's no y-coordinate, it's just 0, so we would actually have no spaghetti there at all. Okay. Let's keep going. I'm going to keep going with this idea. At 45 degrees, how long is my spaghetti going to be? This is going to be about that big. Okay, that looks about right. Let's put that in right there. And then let's do the 60 degrees. And you're kind of hopefully starting to see kind of the idea what's going on here. Alright, 60 degrees, I got that one right there. And I'm going to continue this on. We're going to do one more at 90 degrees. And that guy is going to be about that big. And so you can see the graph is kind of climbing, right? It's climbing up right about there. And if I kept going, like if I had another spaghetti, I'll show you maybe one more. Might be a good idea to do this. Now I'm still measuring now at 120 degrees. Now I'm going to break off spaghetti that's big, about that big. And if you notice, well, 60 degrees and 120, they are going to have the same length of spaghetti, right? So the graph goes up, and then it starts to curve back down, right? Let's kind of draw that shape out the best we can. It looks like something like this, and then it's going to start coming back down. It's going to come back down. Let's go ahead, let's fast forward, let's see the finished product of what it should look like, because if I kept doing this, it would take all day, ladies and gentlemen. So before you see the final product, why did everyone think the spaghetti was flirting? It was just a little too saucy, that's all. So once you've done all that with the spaghetti, this is kind of what it's going to look like with the degree measurements and everything. I'm taking this from a past student. So they plotted their spaghetti and they saw, hey, if I trace a curve, it's going to do this. And eventually, it's going to come back down here, right? Well, again, I have no spaghetti. And if I compare that to my unit circle, right? I keep looking at the vertical distance, right, of my spaghetti, and by the time I get to 180 degrees, it turns into nothing again, like it did at 0. But what happens after 180 degrees is, well, if I look at this, now my y-coordinate is always going to be 0 on my unit circle. And that makes sense. I'm going to have to be going down in the vertical distance, right? So I have spaghetti that's with a length of that, but now it's going to be inverted. It's going to be the other way. So now this graph, as we continue, it's doing what we did in the beginning, but now it's reversed, right? It's coming down here, and it's looking like it's coming back up. If it gets back to 360 degrees, well, that's back to 0, and that's kind of back to square one, right? So that's what our graph is doing, and we're literally getting that. We're literally getting our sine graph from looking at the y, right? The y coordinate of all this, okay? And what two sides, what two numbers are we getting when we do this? Like, what numbers is it kind of bouncing between, right? What's the highest y and the lowest y? Let's talk about that. How do you say goodbye to an Italian chef? Pasta la vista. All right, that's enough with the puns. Let's look at the trig graph. So we're going to start with the sine function. Now, this is what I drew without the spaghetti, right? And this is kind of what was going on, right? So we are kind of focusing on this first half of it. We start here, and what two numbers is this going to oscillate between? Well, it's looking like it's bouncing between 1 and -1. Why is that? Well, again, the longest or the biggest y coordinate we can get on our unit circle is either a +1, and the lowest is going to be -1, right? That corresponds to our y coordinate. And so, those are the two numbers it's going to bounce between. And yeah, I mean, if we consider the other angles too, right, like sine of 30 degrees, that's going to be at 1/2. And if I look at sine of 30 degrees, sine of 30 is about right here. Yeah, 1/2 would correspond to be right about there, okay? And that's kind of what's going on. It looks like a wave. It looks like a wave pattern. It's a repeating pattern, right? It's very periodic motion, just like a circle is, okay? You can also go in the negative angle direction, right? Normally on our unit circle, we measure angles starting from here and we go counterclockwise. To measure negative degrees, we have to go clockwise, right? So negative 30 degrees would actually correspond with 330 degrees, right? And so that would be the same length of spaghetti as 30 degrees, but now it's negative. And you can see that it's going down right here, and yeah, they're kind of like opposites of each other, right? And so yeah, negative 90 degrees, that's the same as 270 degrees positive, and we get a -1 for our y value, and that's actually what ends up happening. So there's some features with this graph as you're getting it down. We get max values at 90 degrees, and we get minimum values at 270 degrees, right? This is repeating. It's repeating just over and over again. 0, 0, the origin is traveled through. That's actually important to note, which you'll see with the cosine graph. And it repeats every 360 degrees. We call this the period of the graph. The period of a graph is how long it takes for it to complete one cycle. And so it takes 360 degrees to do so. Okay. Let's take a look at the cosine graph and see if it's any different. And we'll compare in a little bit. But here is the cosine graph. Okay, now how am I getting that at all? Okay, let's look at that. Well, if I was able to get the distance for my y, and that corresponded with, with my graph over here for sine when I was making it with spaghetti sine, well, the same is true for cosine, except cosine isn't concerned with the y coordinate, it's concerned with the x coordinate. So what I can do is actually rotate this about, okay? And now I can kind of measure how long these guys are going to be going this way. And I can get those measurements right there, okay? And I can plot them. What you need to know, though, more than anything, is kind of the features of this cosine graph. First of all, it's the same thing as the sine graph. It's just offset by 90 degrees. Okay, what do I mean by that? Well, if I compare that to the sine graph, if I wrote my coordinate right here, my xy coordinate right here, that is where cosine would start. It's offset by 90 degrees. So if I take the sine graph and move it by 90 degrees, I end up getting the cosine graph back as a result. Okay, and you can verify this. You can plug in an angle for cosine and see if this is going to be true, and it should be. Okay. 0, 0 was traveled through for sine, but 0, 1 is actually traveled through for cosine. That's actually the start. Why is that? Well, what is cosine of 0 on our unit circle? And cosine of 0 degrees is just +1. But that also means cosine of 180 degrees would be -1. And in fact, that's what happens on our graph, right? So we're literally getting this graph from the unit circle, okay? And obviously it continues on forever and ever. One cycle is the same as sine. 360 degrees is what it takes, okay? Same range, domain, and period as sine. So let's move forward with these, okay? And maybe compare them before we go. They look very similar to each other, and in fact, like I said, this one's only offset by 90 degrees. Okay. So let's start getting some actual things that we can write down other than just the graphs. Okay. Let's talk about what a period is. I said that these graphs have a period of 360 degrees. Definition: it's the smallest interval that contains one copy of the pattern. Right. 360 degrees, 0 to 360 degrees. That's the smallest interval that contains this cycle before it repeats once again. Okay. Sine at 0 to 360 degrees. Cosine is also 0 to 360 degrees. Okay. Now, before we move forward, let's talk about this thing that I want us to add to our unit circle. Okay. So we have in our quadrants A, S, T, and C. So I'm going to label this A, S, T, and C. Why are we doing that, Mr. Knight? Well, let's look. Okay. ASTC is an acronym for All Students Take Calculus. Okay. And basically what that does is it tells us which trig functions are positive by quadrant. Right? So for example, if we look at quadrant 3, this is T for tangent. So that tells me that only tangent functions for angles taken here, right, is going to be positive. That means if I take the sine of angles in quadrant 3, I'm going to get a negative number, a negative value, okay? If I go into quadrant 1, it's all, right? That means every trig function is positive in quadrant 1. Quadrant 4 means only cosine's positive, sine's only positive in quadrant 2. And if you look at your unit circle, that actually is very true. The y is positive here for sine, but it's negative here for this one, just like the x for cosine. So tangent would end up being positive, right? Because a sine over cosine is tangent, and negative divided by negative is a positive. So it actually works out, okay? Add that to your unit circle because it's probably going to come in handy, okay? Now, kind of the meat of today's lesson, what I really want to get at is actually solving equations using these trig graphs. So I want us to solve cosine theta equals 1/2. So go ahead, pause the video, and figure out what what theta has to be in order for cosine theta to equal 1/2. Go for it. Alright, so there's a lot of ways to figure this one out. You could use your chart, you could use your unit circle, or you could use some algebraic moves, right? This is kind of what I'd like you to probably do and at least wrap your brain around as we go. We did this with vectors a bit. Again, if I have cosine theta equals 1/2, I could take the arc cosine theta of both sides. These would cancel. I'd be left with theta equals the arc cosine of 1/2. So theta should actually equal 60 degrees. Okay, that was easy. It equals 60 degrees and 300 degrees, 420 degrees, 660, so on and so forth. It equals that as well. Really? Yeah, it does. Let's pretend for a second that I graph this, okay? And so I take my cosine graph that we saw before, starting at 0, 1, and we got a minimum at 180 degrees, and it's just going to repeat that cycle. And, right, I'm looking for what angle down here is going to give me 1/2, right? Well, if I make a dotted line across, and I figure out where it's going to cross, it crosses at many points. So this was at 60 degrees, right? But this is negative 60 degrees over here. And then we keep going. Here's 300 degrees. Here's 420 degrees. Here's negative 300 degrees back here. There's actually infinite solutions for this, it turns out. So what do we do about that? Okay, that's kind of an issue. And why is that happening too? Let's answer that question first. Why is that happening? Well, sine, cosine, and tangent are many-to-one functions. Basically what that means is as I plug in something for my input, I can get many of those inputs equal one output. So if you thought about it like a mapping diagram, you could think about as a mapping diagram, you could think about it as many going to one. Okay, many to one. So kind of what we were just talking about, right? Cosine 60 equals 1/2, cosine this equals 1/2, cosine this equals 1/2, so on and so forth. The problem with their inverses, arcsine, arccosine, arctangent, they are one to many, which makes it not a function, it turns out. No biggie. There's something we can work around with that, and we're going to talk about that right now. This is where something called principal values is going to come into handy. Okay? Principal values. Principal values are the smallest angles that make up all the output values. And your book actually does an excellent job of illustrating this. So let's turn to that page, and I encourage you to as well. And I encourage you to write this in your notes. The only reason I didn't write it down is because, again, the book does it so much better. Okay? Right here. Here are your principal values right here. We're not going to focus on tangent right now, but let's look at cosine theta and sine theta. So in the blue, these are your principal values. What does that mean? Well, that means those are the angles that we could use to get every single possible output. Right? This thing's only going between 1 and -1 the entire time. So for cosine, for example, we only need the angles from 0 degrees to 180 degrees to get everything from -1 to 1 to get our entire range, right? So it's like the smallest domain that lets us get our full range. Same thing with sine, right? If I want to get my full range from -1 to 1, well, I have to go from -90 degrees to +90 degrees, okay? And those are the principal values, and we can write those down as well. Those principal values. Go ahead and you can write down the tangent one. We'll talk about that one tomorrow. But I want you to focus on cosine and sine, right? This is exactly what we just said the principal values were to make up all the output values, okay? And so we're going to use that to our advantage, okay? For our first example, we're going to find values of theta in the interval -360 degrees to +360 degrees, for which sine theta is equal to 1/2. Okay? There's a couple things we can do about this. Okay? Like we said before, sine theta equals 0.5. If I want to solve for theta, well, that's a lot of different angles. And I want to find out what all those angles are to where I plug it into sine and get 0.5. I want to find what those angles are between -360 degrees and +360 degrees. So you can graph it. You can graph your sine graph and just see what's going on. Or you can use the unit circle. And I actually recommend you use the unit circle. I think it's a little bit easier in this case. Because we already did see the graph and kind of what that looked like, right? So you can throw the graph in Desmos and see what values are getting you 0.5 for your y value. Or we could do the unit circle. So I know that sine theta equals 1/2. I know that the angle that gives me 1/2 for sine, well, it's going to be the y value right here, right? So 30 degrees is one of my angles. When I take the sine of it, I get 1/2, right? Well, what else is going to do that, okay? Well, let's keep going around the unit circle. And remember, these blue correspond with each other, right? So this angle and this angle actually have the same y value, it turns out. So 150 also gives me 1/2. If I take sine of 150, I also get 1/2. So those are two of my answers, right? But I want between -360 degrees and +360 degrees. So right now we're just doing from 0 to 360. Okay? And in fact, that's everything we can get from 0 to 360. Right? It's 30 degrees and 150 degrees. Those are our two answers. Okay? Let's go the other way though. Okay? This is where it might get a little tricky, but think about it like, think about as you're going. -90 degrees is right here. Okay? So we actually we don't want these ones right here. I know they're blue, and they give us the same value, but they give us negative 1/2, right? So that's why I didn't even include those when I was going positive, okay? So I want to skip those. So negative 90, negative 180, and now I want to get there. Well, to get there, that's an extra 30 degrees, so negative 210 degrees is my other angle. And I have one more if I keep going. I end up here. This is at negative 330 degrees, okay? And in fact, those are my 4 answers right there, okay? The unit circle is really useful for this. The graph is nice, but I think the unit circle is a little bit better for these types of problems. But the graphing, of course, has its use. Knowing how the graph works is going to be part of our homework, okay? So let's go on to the next example, okay? This guy right here. Here's our next example. We are going to solve the equation 2 sine squared theta equals cosine theta plus 1 for angles between 0 and 360 degrees. So when we start this problem out, I would really like everything to be in terms of one trig function. That would be nice. Dealing with multiple at a time is kind of frustrating. Luckily, I know what this guy is in terms of cosine. Using Pythagorean's identity, I know that sine squared theta is the same as 1 minus cosine squared theta. So I replace it with that, and now I can distribute the 2. When I distribute this 2, again, cosine theta and cosine squared theta, they're kind of like x and x squared. They're not like terms. I can't combine them, but I can make it look like something I'm used to working with. Maybe like a quadratic, right? Yeah, let's make it look like a quadratic, okay? So that's what I do, okay? I move everything over to this side, and so I get 2 cosine squared theta plus cosine theta minus 1. And now, like I said, I could treat this like a quadratic. Now, when we work with quadratics, usually we work with x and y. Let's just pretend or declare that x is equal to cosine theta. So I'm going to rewrite this as 2x squared plus x minus 1 equals 0. And now I'm going to factor that just like I normally would. You can use the x method, the slip and slide method, whatever method you think is useful, or you might be able to just look at it, right? And so those are my factors. And now, instead of x, remember, x is cosine theta. So that's what I'm going to replace it back with, okay? And I'm going to get 2 cosine theta minus 1 equals 0, and now cosine theta plus 1 equals 0. After I rearrange some stuff, this is what I end up getting. Now, it comes down to, all right, what angle for theta makes this true, right? Or what angles? And what angles between 0 and 360 degrees? That's all we're looking for. So, again, I would consult with your unit circle, for sure, okay? Let's start with 1/2 for cosine. Well, which angle, when I take cosine of it, gives me 1/2? So we're looking at the x values, and it looks like 60 degrees, so cosine 60 degrees gives me that. It also looks like cosine of 120 does, except we're looking for positive 1/2, right? This gives us negative 1/2. So where else does cosine give us a positive value? All students take calculus quadrant 4 right here. And in fact, this 300 degrees is the other answer. This is where it's also 1/2, right? So there we go. I know it's at 60 degrees and 300 degrees. And that's between 0 and 360. Okay, what about when cosine theta is equal to negative 1? What does the angle have to be? All right, let's find where it's going to equal negative 1, and it would be right here at 180 degrees. So the other angle I'm looking for is 180 degrees. Both of these are answers. So that means my angle up here can be any of those 3 angles, and that would solve the trigonometric equation. Okay, that's kind of the bread and butter of what I wanted to get to today, is solving these. And get a little bit comfortable with graphs and seeing graphs. We're going to be focusing specifically on graphs more tomorrow with the tangent graphs, but I wanted you to get some practice on your belt, see where it comes from, and then see how we can use it with the unit circle. This is Mr. Knight, signing off. Hope you enjoyed those pasta puns.